Welcome back, everybody, to Math 1314, more on math. Today we're going to talk about Chapter 5, Section 3. Section 3 deals with logarithmic functions, or logs, and their graphs. Today we're going to find the common and natural logs. And then we're going to convert between exponentials and logarithmic equations. Then we're going to talk about change of bases and why we do those. And then we're going to talk about the graphs of the logs. Alright, let's begin. Recall from last section. E to the power x, or a to the power x, that's more like it. We had conditions. A had to be positive, a could not equal 1, it was 1 to 1, and because it was 1 to 1, it's continuous, and that means it has an inverse. So an inverse does exist. Well, that inverse, if f of x equals a to the power x, its inverse is the log. This is the notation that we'll be using for logarithmic equations. Remember, a was the base, it's still the base. Here's the exponent, here's the operation. So, the way this is read is log base a of x. That's how it's read. So, okay, our last example we had a equals 2. So if we had log base 2, let's say of 8. Okay, this is read log base 2 of 8. That's how you read it. But what it means is more interesting. What this means is this is what it means. What power do we raise the base 2 to equal 8? That's what it's looking for. So log base 2 of 8 equals some number. We don't know what it is. And we're going to learn that to figure this out, we know that it's going to be 3, plus 2 to the power 3 is 8. So we're going to know that x equals 3. We're going to show you how to do that in a minute. So, okay. Logs can have any base. Okay, so logs can have any bases. All right. if we had base 10, base E, and base anything else. All right, so if we had log base 10, think about it. Our counting system, we have a decimal counting system. That's base 10. That's why this is called a common log. Whenever you hear the word common log, you know it means base 10. So log base 10 of x. Since it's a common log, we don't have to write the base. Notice, if there's no base, it's automatically base 10. Base E, remember that's Euler's number. We call that a natural log. Remember, E came from the equation itself, naturally getting a value. So that's what we call it natural log. So log base E, since it's a natural log, we write it ln. Whenever you see ln x, that means it's log base E. And anything else, that number has to be there. All right. So that's the different types of symbols we use. That's how come we see a lot of textbooks. They use these two symbols because it's much easier to write. All right. So that we have that. Now, conversion. We're going to look at going from logs to exponents, or from exponents to logs. And this is how we help to solve these things. So, you begin with an equation. Log base A of x equals y, some number y. Remember, this is the base. It has to remain the base. So this is logarithmic. We have to know exponentials. Remember, we had our base A. So what happens here is the A comes to the other side and pushes up the y. Now, if the base is gone, the log falls off, so we're just left with x. There's the conversion. Log base 2 of 8 equals x. Converting that, we get 2x equals 8. All right, so now we said let's solve this thing. Whenever you compare these things, you have to make sure you have the same bases. What is 8 made up of? 2 times 4. So 8 is actually 2 to the third power. Since the bases are equal, the only way they can be equal is if we have the same exponents. That's where we got our 3 from. All right, let's look at some more examples. So here's some more examples. Log of 10,000. Remember, log, if it has nothing below it, it means it's log base 10. So that equals some number x. So the 10 comes over here. 10 to the power x equals 10,000. 10,000 is 10. 1, 2, 3, 4 zeros. Since the bases are the same, x equals 4. So this answer is 4. How about another one? Log of 0.01. No base, so it's log base 10. That equals some number x. 10 to the power x equals 0.01. 0.01, since it's a decimal, that means it's a negative exponent. 1, 2. So here, x equals negative 2. There's some more examples. Now let's look at, our answer could also be a fraction. Log base 9 of 3 equals some number x. In a question, you'll just be given this. You'll just be given that. You have to put the equals x. So the 9 pushes the x equals 3. Remember, we have to get a common denominator. It has to be the same base. So what is 9? So 9 is 3 squared. And we talked about exponents in chapter 2. Whenever you have power to a power, you multiply. So 2 times x is 2x. And since there's no power, it's automatically a 1. Since the bases are the same, we just worry about the exponents. Solve for x. So x equals 1/2. So our answer for log base 9 of 3 is 1/2. How about log base 6 of 1? Remember, log base 6 of 1, we put the equals x. 6 to the power x equals 1. The only way a number can equal 1 is if x is 0. So whenever you have a 1 there, it's automatically going to be 0. What if we had log base 8 of 8? If the base of the number are the same, what happens? So log base 8 of 8 equals x. The 8 pushes the x up. Equals 8. That has a power. So x equals 1. So whenever the base and the number are the same, it equals 1. Which those last two are some of our properties we're going to talk about next. Let's go the other way. So what if I gave you 16 equals 2 to the power x? Put that into exponential or logarithmic. Remember, our conversion is log base a of x. A to the power x equals y. So there's your base. It has to remain the base. And whatever the exponent is, actually it'd be log base a of x equals y. So it's a to the y equals x. So whatever your exponent is your answer. And whatever the answer is here is now inside the equation. So they just switch places. So there's your answer. How would you write this one? Remember, the base is e. That's log base e. That's ln. So we're going to use an ln function. So ln of 70 equals x. Or you could have done from here, since e is your base, log base e of the answer equals the equation. Log base e is ln. Either way could have worked. All right. Oh, your calculators are limited. Your calculators are limited. What does that mean? On your calculators, you only have these buttons. You only have log base 10 or log base e. There is no log base anything else. So if I gave you a question like this, log base 2 of 3, you could not find it on a calculator. So what we need to use the change of base formula. We have to change it from base 2 to either one of these guys. The way you do that is this way. Here's a formula for it. ln, whatever a is, and so whatever's on top goes on the first one. Whatever's on the base goes to the bottom one. So now these are both log base 10s. You can use a calculator. Or if you wanted to, you could use the ln function. Because it's not the actual numbers, it's the ratio of the numbers that's going to give you the answer. All right? So that's pretty important when it comes to that. So whenever you have a base other than 10 or e, if you use a calculator, you have to use the change of base. The graph of ln x, or a logarithm, remember, the exponential equation, its graph looked like this. The logarithmic equation Because it is the inverse. It is the inverse of the exponential function. Remember what inverse means? Is you switch x and y. So this point here used to be 0, 1. Or it is 0, 1. So that means on this graph, we have to switch the x and y. So instead of having a y-intercept, we have an x-intercept at 1, 0. Since this one here, you couldn't have any negative y's, on this one, you cannot have any negative x's. This graph looks like this. Again, you can use a table if you want to. Let's say log base 2 of x. Plot some points. You use positive and negative numbers. Same thing there. It's always going to look, it's going to have the same basic shape each time. We also have transformations. Again, because it's easy, I'm going to use the ln function. It's easy to write, not because it's easy to calculate. A horizontal shift. The origin shifts from here back 3 spaces. So we have the new origin there. The y-intercept used to be at 1. Now it's 1 to the right here. I have the x-intercept, I mean. X can never be negative, so inside there cannot be negative. That's how come we shifted to the left. If x is negative, this number here, logs cannot take any negative values. So the smallest it could be is, if x is negative 3, it's 0, and you can't have that. It has to be positive. So what this one means, this is the vertical shift. It goes up 3 spaces. So here's your new horizontal line. ln x looks like this normally, but it turned out to be negative. Because the function is negative, again, it still crosses at 1 to the right. What that means now, instead of going up, it's now a decreasing function. Wait. I ran out of space there. Let me show you this one. So let's do it piece by piece. First one, ln x. Looks like this. Again, the asymptote is a vertical asymptote. It crosses through 1. One half ln x. Remember the intercept for this one is 1 times a half. What this one does is it shrinks it. So when x is 1, it's still going to be 0. Right? When x is 1, it's still going to be 0. But it grows a lot slower. Instead of 2, 1, it's now going to be half as fast. The negative in front changes its direction. It's now going to go like this. It flips across the y-axis. And the 3 in front is a vertical shift. 1, 2, 3. So here's your new horizontal line. It crosses at 1, and there's your graph. So those are the graphs and what it basically looks like. Again, you have to get more accurate, use your calculator. I'm pretty sure that's what they're going to want on the computer. But this is the basic shape of it. All right, good luck.